You know those massive AI models we hear about all the time? The ones with billions of parameters? Well, training them is one of the biggest challenges in computer science. It takes just colossal amounts of data, time, and energy. But what if I told you there was a completely different way to do it? A method that's inspired by nature, and that could be over 100 times faster. All right, let's dive into EGRL.
I mean, really think about that for a second. When you have a model with billions of connections, how do you even begin to teach it? You can't just throw data at it, right? You have to figure out how to adjust every single one of those billion connections to make the whole thing smarter. And that is the huge problem researchers have been trying to crack.
So, for decades, the go-to method for this has been something called backpropagation. The best way to think about it is like a super meticulous teacher. After a wrong answer, this teacher uses calculus to figure out the exact, precise little tweak needed for every single connection to get just a tiny bit closer to the right answer. It's incredibly powerful, for sure. But man, is it rigid.
Okay, but what if we just toss that whole idea out? What if instead of painstakingly calculating every single step, we just took a cue from millions of years of evolution? What if we just tried a whole bunch of things and saw what worked? Well, that's the core idea behind a method called evolution strategies. Evolution strategies, or ES for short, is honestly beautiful in its simplicity. You just take your base AI model and you create thousands, maybe even millions, of slightly different versions. Think of them as mutations. Then you throw them all at the same task and see which ones perform the best. You take the successful traits from the top performers, combine them, and boom, that's your next generation. It's way less about precise calculation and way more about survival of the fittest.
And this gets at a really fundamental difference between the two. Backpropagation is a white box method. It has to be like a surgeon, seeing the entire inner workings of the model to do its complex math. But evolution strategies, it's black box. It doesn't care how the model works on the inside, it just gives it a task, checks a result, and gives it a thumbs up or a thumbs down. And that simple difference means you can use ES to train all kinds of wild models that backpropagation can't even touch. Keep that in mind, because it's a huge deal later.
So you're probably thinking, okay, if this ES thing is so flexible and powerful, why aren't we using it for everything? Well, there's a catch, a big one. When you try to apply it to models with billions of parameters, it hits a massive, ugly wall. The traditional way of doing ES just completely falls apart at that scale.
The researchers behind this paper put it perfectly. The problem is something called low arithmetic intensity. Fancy term, but it basically means your system is spending all its time moving data around instead of actually doing the math. Your super powerful GPUs are just sitting there, twiddling their thumbs, waiting for the next truckload of data to arrive. The data shuffling completely overwhelms the actual work.
And here's why that happens. For every single one of those thousands of mutations you want to test, the old method has to create and move a full, separate copy of the model's billions of parameters. Imagine a delivery service where, after dropping off just one package, the truck has to drive all the way back to the warehouse to start over. It's a logistical nightmare, just unbelievably inefficient.
And when you look at the numbers, it's just sad, honestly. A traditional method like OpenEase uses less than 1% of a modern GPU's potential power. We're talking 0.41%. All that incredible hardware is just sitting there, starved for work because of this data bottleneck. So how do you fix it?
This is where the breakthrough comes in. The researchers developed a brilliant new algorithm they call egg roll, and it's a super clever solution that completely smashes through that hyperscale wall by totally rethinking what a mutation even is.
So instead of randomly tweaking every single one of the billions of parameters, EGRO makes small, highly coordinated changes. Think of it like this. Traditional ES was like giving a million painters a single pixel each to repaint on the Mona Lisa. It's chaotic. EGRO is like getting all of them to coordinate on making tiny, specific adjustments just to her smile. It's a vastly more efficient way to find improvements. And the process is just so clever and simple. You start with your base model, but instead of copying the whole thing, you just generate these tiny, efficient, low-rank change instructions. And because these instructions are so lightweight, you can test thousands of them all at the same time on a single GPU. Finally, you just take the instructions that worked best, combine them, and apply that update to your main model.
So what does all this cleverness get you? How about this? For those massive billion-parameter models, EGROL delivers a 100 times increase in training speed. That's not a typo. 100x. Tasks that were just completely impossible before are suddenly on the table.
And remember that pathetic sub 1% efficiency from before? Well, check this out.
EG-roll takes that number and blasts it all the way up to 91% of the hardware's maximum theoretical speed. It basically eliminates the data bottleneck, finally letting the GPU do what it was born to do, compute. This isn't just an improvement, it's a total game changer.
Okay, look, a 100x speedup is awesome, but that's not even the most exciting part. The real story is what this new capability unlocks. Because remember, eGrow is a black box method, and that opens the door to training entirely new kinds of AI that we could only dream of before.
For instance, the researchers used eGrow to train a complex language model that works entirely on simple integer math. Now that might sound a little technical, but trust me, it's a huge deal. Most AI models need complex, energy-hungry floating point numbers. An integer-only model is way more efficient, which means it can run faster on much simpler hardware. We're talking smartphones, smartwatches, you name it.
And it's not just about building new kinds of models, it's also amazing at making the ones we already have smarter. They showed that EG-roll is a powerhouse for fine-tuning large language models, making them significantly better at tough reasoning tasks, like solving math word problems. And they did it faster and more efficiently than other methods.
And honestly, the list just goes on. EGROL is like a whole new Swiss Army knife for AI researchers. It can dramatically speed up reinforcement learning. It can fine-tune AI agents for super complex stuff like high-frequency trading. And it's perfect for optimizing those weird hybrid models that have parts that calculus-based methods just can't handle. It can even take a giant model and distill it into a much smaller, faster version without losing its smarts.
But the team behind eGroll is thinking even bigger. They see this as a key to building much more sophisticated AI in the future. Things like training complex systems where a neural network can interact with a calculator or a database, or even training swarms of AI agents that learn to cooperate in really complex environments. So, let's bring it all home. What's the big takeaway here? eGroll isn't just about making things faster, it's a fundamental shift. By finally making evolution a viable, practical strategy for training massive models, it unlocks a whole new design space for AI. It's about opening up a whole new playbook for how we design and build artificial intelligence.
And that really leaves us with one massive, exciting question. For so long, the sheer cost and difficulty of training has been a huge bottleneck for our imagination. But now that a method like eGroll has come along and smashed that barrier, what new, exotic, and powerful kinds of intelligence could we finally evolve?